Hello, today we're going to work on lesson 3.2. So in 3.1, we just learned a lot of really cool things about quadratics, which are special polynomials. And now we're going to learn some general things about polynomials in 3.2. So let's actually, I'm going to share my screen. And if you can have your book open to page 230. To page 231. So in 231, it gives the definition of a polynomial. And this is important to pay attention to. Polynomials have many nomials or many terms, more than one term. And the key is their exponents, and it says n is a non-negative integer. So the exponents cannot be negative and they can't be fractional. So that's something to pay attention to. They're all real valued constants. And the domain is the set of all real numbers, so something else to pay attention to. So we have to go back and remember some important things about terms and degrees. So the degree of the polynomial is the highest degree in the polynomial. That's the degree of the polynomial. And then we have to make sure we go back and remember that terms are constants and variables that are being added or subtracted. The leading term is the term that has the leading highest degree in the exponent. And you could have a constant polynomial where it's just f of x is equal to 6, which is just y is equal to 6. Okay, so we're going to also go to look at here a couple examples here on page 232. Make sure that you're always using your book as a reference, because sometimes I do examples that don't exactly match the problems that you are being assigned, but there are good references in your book as well. And all of the odd questions should have answers in the back of your book. And I do assign some of those. Okay, so on page 232, it gives 4 examples of graphs you may see, and some that are polynomials and some that are not. So this picture here, the first one on the left, is an absolute value function that has been translated or transformed and reflecting over the x-axis. This is not a polynomial. It has a corner here. The second and the third ones are polynomials. You can see that they're smooth, even though they kind of curve up and down. They're smooth. And we're going to learn about what tells you it's going to be facing down or facing up, or both of them down and one up. But the last one is not a polynomial because there's a break in the polynomial. Okay, so we learned a little bit about transformations back in a little bit in chapter 2, and then in chapter 3.1 we learned about transformations of specific polynomials, which were quadratics. And you can see here in this graph, we have your basic, this is an x to the 4th. And it looks a little bit different than your x squared. And x squared is going to be more of a perfect U. And this is like a really wide U. Then you can see that the red here is an x cubed. So we're taking note on some of these. So it says here, an odd positive integer, you have in the domain all real values, and your range is also all real values. But what's interesting about the end behavior, in an odd numbered exponent of the highest degree, notice that part of the shape of the graph is going down and part is going up. So they end in opposite behavior. When the exponent, the highest degree, is even, you can see that the domain is still all real numbers, but the range is, the base range is from 0 up, because you can see that in blue, the entire shape is facing up, we'll say. Okay, so the evens are both facing the same way. Notice that to the left and to the right, they're both facing up. The odd, this x cubed, one is going down and one is going up. So odds have opposite behavior, evens have the same. Okay, so I'm not going to have you do any fixed transformations because you can use Desmos, and we are going to show some things in Desmos today. So you can see here the leading term test for end behavior. You can see that they're both negative 2x cubed and a negative 2x cubed, but the second one has this plus 8x on it. And so here is our leading term and behavior test. So it says, given the polynomial, the end behavior of f is determined by the leading term. So you can see that they both have a leading term of negative 2x cubed. The x cubed tells us that part of the graph is going to be facing up and part's going to be down. And so you're wondering, how do I know if it's the first part is up and the last is down, or if it's flipped, like the one that we looked up here, where the first was down? So it goes by the coefficient on the leading term. So on this one, the coefficient is a negative and a negative here. That means it's going to end in the negative way. And when it's a positive, like the one we looked at up here, it was just x cubed, so it was a positive 1, which means it's going to end in the positive way. So that's pretty cool on the end behavior. So you can see the example here on page 234, that the leading coefficient on A is x cubed, and it's a positive x cubed. So that means it's going to move in opposite directions, and it's going to end in a positive way because it's the coefficient on the x is a 1. And you should be able to see that here in the graph here. Their graph did not show that. We're going to see that. So I'm gonna type in this x cubed plus 3x squared plus x for A here in the index, so you can see. So you can see that it's doing a couple turns. We're going to learn about how many turns it's going to take in just a little bit. It gets so exciting. And you can tell because the leading exponent is odd, so it's heading in opposite directions, and it's going to end facing up. It's ending up. And that's because there's a leading coefficient of 1 on the exponent. So let's go ahead and just save this for and I'm just going to say leading coefficient is 1, so it ends facing up. And up to 3 is common. So one up, one down is how I say that. One up, one down. Okay, so okay. Now, so, but let's look at the other one. That's the example 3b. And so we're going to take that one in, and that's negative 2x to the fourth. So if you want to get practice right along with me, it's all very worth it. So negative 2x to the fourth. Remember, I'm using x's because you don't have t's. Also, remember over here that I can turn off my blue one for a minute. And you can see that this one's got a bunch of crazy terms. But you can see that because, let's go ahead and add a note here that leading, let's just copy what we have up here and add to it. So the leading coefficient here is negative because it's negative. That's the key. It ends facing down, okay? And the degree equal to 4, the leading degree, the degree is 4. So both face the same way, okay? So that's the key. Now I'm going to add something new here, which I think is super cool. We'll go back and look at the other one. You're probably wondering, like, how do I know how many turns it's going to take? So because it's a 4, so let's right here. The number of turns equals degree minus 1, which for us is 4 minus 1 equals 3. So let's look here. There's 1, look where my mouse is. There's 1, it comes down 2, 3. So that's what's going to tell you. And it's going to be at most. The number of turns equals degree. Let's put this at most. So it won't always. But we're going to also learn about that. How many times it's going to touch the x-axis. So this is so cool. Let's go back up here. Let's add this one. This is the example. 3A, page 234. Oops. Okay. So this one, I'm going to turn off the purple one and I'm going to turn this blue one back on again. So you can see, and it has 1, 2 turns. It goes up and turns once here, once here. And that's because the number of turns is the degree minus 1. The degree minus 1, which for this one is 3 minus 1. So there's at most 2 turns, and we happen to see them. Okay. So I also want to, let's just factor this while we're here. This is like such a cool opportunity to be able to see. So factor above polynomial. And when we do that, we get x parentheses, because x comes out, and then we get an x squared plus 3x plus 1. But that will not factor anymore. Okay, so so that tells us that either x equals 0, that's one of our zeros, we know that, or that this right here equals 0. And so you can see that our zeros here, one of our zeros, if I click on the graph, see there's the 0, 0, 0. And then here's the other one that's irrational, and that's because it doesn't factor. So if you can't factor a polynomial into integer, just our factoring that we do, then it means it still has zeros, but they're irrational. So see this one, it's an irrational one, meaning that it's not an even terminating decimal. It's not an integer factor is what I mean. So that is pretty cool. Yep. And it's going to have 3 zeros. 1, 2, 3. Okay, I'm going to turn that one off again and go back to the purple one because I'm going to zoom back up for a minute. So we can see that it's got a degree of 4, so it's going to turn 3 times 1, 2, 3. And then let's just factor this. Factor above. And when we factor it, we can take out a negative 2x squared, right? And when we do, we have x squared minus 4. Okay, so what's cool about that is that that actually factors into the negative 2x squared parentheses, and then we have a difference in squares of x minus 2, x plus 2. So that means we have x minus 2, x plus 2 are going to be net at zeros at 2 and negative 2. So let's go ahead and click on the graph. And you can see, yep, we've got negative 2, 2, and then we've got the 0 because this first piece equals 0, negative 2x squared equals 0. So I'm going to show you on my paper so they don't show you this in the book, but I just think it's pretty cool. Okay, so I'm going to go and show you my paper here. I just love being able to pull all these pictures. So this is the one we just did in the book. We use x's because that's what Desmos likes. Okay, so degree equals 4, even. So it's going to be either both up or both down. Okay, and because leading coefficient is equal to a negative 2, which is less than 0 because it's negative right there. Because it's negative, it's going to be this one. It's going to be facing down. And we saw that. Okay, they're both facing down. So make sure you're not forgetting that. Okay, so then we want to factor it and see what else we know. So I'm going to show you the factoring here just because you can't draw in decimal the exponents as well. So a negative 2x squared comes out, and then we have x squared minus 4. And so we have a negative 2x squared, and then this is our factoring into x minus 2, the conjugate's x plus 2. So we have, because we have 4 is our exponent, we have 4 zeros. So also means 4 zeros. And that's the x squared means that the 2 on the x. So minus 2x squared equals 0. If we divide by a negative 2, x squared equals 0. Because this is an even multiplicity, is what we're going to call that right here. It's an even multiplicity, then this 0 counts as 2 of the 4 zeros. So x equals 0. And then this one here, x minus 2 equals 0. X equals a positive 2. It only has a 1 multiplicity on that 0. And then this only has a 1 multiplicity as well. X plus 2 equals 0. So x equals a negative 2. So this counts as 2. This counts as 1 and 1. So there's our 4 zeros. Isn't that so cool? Things that you're like, what? I could tell that just from all of these things. It is so cool. Okay. So the multiplicity thing comes up on page 237. So let's go there in the book for a moment. So that you all can see the multiplicity thing right here. So the number of times a linear factor x minus a occurs in the completely factored form of a polynomial expression is known as the multiplicity. Okay, so their example here says x plus 1 times x minus 3 squared. X plus 1 has a multiplicity of 1, so x equal to negative 1 is one of the zeros, and x minus 3 squared, see that when you factor it, it happens twice. So it counts as 2 of the zeros. It's so awesome. And so you can see that when it has an even multiplicity, it comes down and just touches at, or comes up and touches at that 0. If it's an odd multiplicity, it crosses, it cuts through. So that's on page 238, important to maybe have written on your little note sheet that you can use on the exam. Okay. Then the last little bits that we're going to talk about today is the symmetry of polynomials here on page 239. So this symmetry here is like example 7. It says x to the 4th plus x squared plus x is odd, even, or neither. So it says because x has some even power terms, we will check to see if it's an even function. So you can see that it's not exactly even, because you should be able to put in the negative of x in there and still get the same function. But we don't. We end up with a negative x here on the tail end instead of a positive. And it's not odd either, because the opposite of a negative x doesn't come out to be the opposite. So then the local maximum minima, but those are the turning points that I mentioned, okay? So the local maxima is if you go up and have a turning point, and a local minima or minimum is when you go down and have a turning point. Those are kind of natural to see. We're going to be pointing all those things out, okay? So on this graph here on page 241 is the example. Here on example 8, it has a negative 2x to the 4th plus 8x squared. And so you can find the y-intercept, which is by putting in 0. That means you're going to be at 0, 0. And then by factoring out This is the one that we just did from example 3, we factored out. And so we have a multiplicity of 0, 2, a multiplicity of 2 for x equal to 0, it happens twice, and then a negative 2 and 2, so those are our 3 zeros. Our symmetry is an even function, meaning that if you put in x or negative x, you will treat the same thing. And then our test values for the integrals just to determine the sign of f in the table. So just looking for where it's turning. So, and so basically we're just looking at the intercepts, like where is it turning at? And then you can know that it's going up or going down. Okay. And we already talked about the zeros based on the multiplicity. So that's important just to touch on here on page 241. The number of real zeros of a polynomial of a degree n is less than or equal to n counting multiplicities. The graph of f can cross the x-axis at most n times. Okay, so if c is a real zero of a polynomial, that is the function of c is equal to 0 and c is a 0 multiplicity k, then we know that c comma 0 is an x-intercept of the graph and x minus c is a factor of f of x, but the factor x minus c to the k plus 1 is not. So if x minus 2 to the 1 is a factor, then we know that x minus 2 to the 2 is not a factor. That can't be. So these are just some extra examples here. Okay, so it's important to remember the number of real zeros of a polynomial of a degree n is less than or equal to n, counting multiplicities. The graph of f can cross the x-axis at most n times. Okay, so let's go ahead to my paper and we're going to do some examples in the book. So if you can get out your, open up your book to look at problem number 9. We're going to look at starting at number 9 here. And 9 and 10 are both pictures. So 9 says, determine whether the graph represents a polynomial and explain your reasoning. And yes, 9 does, because it's smooth curve, there aren't any gaps. And so yes on number 9. Number 10 is no, it's not a polynomial because it has a corner. It can't have a corner. Okay. Yes. Smooth. And 10 is no, because it has a corner. Now I'd like to look at 15. 15 is the function of the square root of t. So we have to go back to our definition of polynomial because the exponents have to be integers, we said. And this is actually t to the 1/2. That's what the square root of t is. So this is not what we need. So no, it is not a polynomial. because it's a fractional exponent, so it's not an integer. So let's look at 19. 19 is f of x equals negative of x plus 1 cubed. And this is the same as the negative of x plus 1 times x plus 1 times x plus 1. And if we multiply this all out, we will get all integers. So yes, it is a polynomial. Okay. Let's look at number 24. So 24 is g of x equals 3x to the fourth plus 2x squared minus 1. And it's just asking for the end behavior. So end behavior means that we have degree is 4. So it's this or it's going to be this. They're either both down or both up because it's even. And the 3, the leading coefficient is positive. It's greater than 0. So it's going to be this one, face up, because it's positive. So that's our end behavior. If you put this in the decimals, you will see that they both face up. Isn't that so cool that you can tell that? I think it's so awesome. Okay, so let's go to problem number 27 is the next one I want to look at in our book here. Let's look at 27 is g of x is equal to a negative 10x cubed plus 3x squared plus 5x minus 2. So I want you to think about the end behavior. Take a minute and do that. Okay, so you have a minute to work on this. So it's asking for end behavior. So again, we have our degree is equal to 3 and our leading coefficient is equal to a negative 10, which is negative. So our degree is odd. So that means it's either going to be end facing up or end facing down. And because our leading coefficient is negative, it's going to end facing down. Isn't that so cool how we can tell that? So we're going to flip the page. We're going to go to some higher problems. And I'd like us to look at number 66. It's in the book. And show you. So 66 is this graph here. And it says part A up here, they want us to make sure you're looking up here. It says they want us to find the x-intercepts. So that's where we're crossing the x-axis. So it looks like at -3 and -1. B is the y-intercept, which is right here where we're crossing the y-axis at 0, 5. Whether the leading term is odd or even, they're both face up. So they're both together. So it's even, and the sign of the leading coefficient. And because they're up, it means the leading coefficient is positive. So let's write that down. Okay. So A is the x-intercepts. B is the y-intercept. The x-intercepts were at -3 and 0, and then 0, 0, -1 and 0. Our y-intercept was at 0 and 5. And C was the odd or even, so it's even powered. because it was both facing up. And D is leading coefficient is greater than 0, it's positive. And that's because it's both facing up. Okay. So that's cool that we can see that just from the graph. So on number 68, it says, determine the real zeros of the function and their multiplicities. Comment on the behavior of the graphs. Does it cross or just touch? Okay, so this is how I like to do these. G of S equals S plus 6 to the 4th and S minus 3 to the 3rd. Okay, so our zeros are going to be at S plus 6 equals 0. So that would be at negative 6. And then S minus 3 equals 0, which is S at a positive 3. And because this is even, okay, it's going to touch. And because this is odd, it's going to cut through. Okay, so we can imagine a graph. It says you can check your with a graphing utility. So let's imagine, let's see if we can do it on paper, and then we'll go check it on Desmos. And because the coefficients on this S and this S are 1, so it's positive. So the leading coefficient is going to be 1. Will be positive. And because the degree is 4 plus 3, which equals 7, and it's odd, it's going to be ending up, and it's going to be this. Okay, so we know there's one at a negative 6. We know there's one at 3. It touches, it cuts through and it faces up. So we know it cuts through here and faces up. Okay, and it touches at a negative 6. And because we know that it excuse me, we know that it goes up and comes, it starts down and ends up, see over here where my pencil is, my pen, and it touches at a negative 6. This is what I'm thinking. It comes up, it touches at a negative 6, it comes down and does something. We know, let's look at the y-intercept. Is going to be 0 plus 6 to the 4th times 0 minus 3 to the 3rd. So this is going to be 6 to the 4th times a negative 3 cubed. So this is going to be extremely large. We don't even need it in the negative way, because this is going to be 6 to the 4th times a negative 27. So this is going to be extremely negative. So this is what I'm thinking. It's going to come up, touch at a negative 6. It's going to go down so far and cross this y-intercept somewhere and then come back up. Okay, so let's check it out on Desmos real quick. I'm just going to make a note. And don't worry, I'll post a link to our Desmos in and this is number 68. Oops. Number 68. So it's going to be y equals x plus 6 to the 4. And then x minus 3 to the 3rd. Oh, we did a bunch of stuff. X plus X plus 6. Oh, I gotta turn off this other graph here. There we go. Okay. So indeed, if I click on it, it does touch at -6, crosses at 3, just like we thought. And it's, I mean, so far down here. It's, because we know that number is so big, because I can put in that y-intercept value right here. It's 6 to the 4th times a -27. Yeah, the y-intercept is at a -34,992. That's crazy. Okay, let's go back to my paper here. Let's look at another problem. So let's look at 76. We're getting really good. 76 is h of x equals 2x to the 4th minus x squared plus 2. And it's asking us to decide if it's odd, even, or neither. Determine the symmetry, if any, of its graph. So it's going to be, is it odd or even? So we can just go to Desmos here and put that one in, because that's a nice way for us to. Let's turn that one off. And this is going to be number 76. Y equals 2x 4 minus 2. Okay. So, so we can click on that and just go up to the gear and have it make a table. And so the cool thing is you can see when you put in a -2, you get 30. And when you put in a +2, you get 30. And that tells us that it's even. And you can see visually that it's symmetric. So 76 is even. I'm just going to look at even function. And then let's look at 78. While we're here. And let's tell what that is. That one is 78 is y equals x to the 3rd minus 2. So I'm going to turn off the blue graph here for a minute. So let's look at this. It looks like it could be odd, but again, let's go to the gear and look at the table. So when we put a -2 in, we get a -10. And then when we put in 2 in, we should get the negative or a +10, but we don't, we get a 6. So it's neither. Okay. So let's go back to my paper. So that was 76 was even, and 78 was neither. Let's look at 84. 84 and 92. 84 is a graph again. So it says use the graph of the polynomial function here. Use the graph of the polynomial to find the real zeros of the function and to determine whether they are of even or odd multiplicity. Okay. So we can tell that there's one at a -2 and there's one at 2. And because at -2, it comes down and touches, it's an even multiplicity. And at 2, it goes through, it cuts, so it's an odd multiplicity. So this one is an even, this was an odd. So x equals a -2. So if we make that into one of the factors, it would be x plus 2 equals 0. And we said this one touches, so even multiplicity. And then the one at x equal 2 is really x minus 2 equals 0 is cuts, so odd multiplicity. And let's look at 92 is another exciting one. So number 92, let's just jot it down. F of x equals x minus 1, x plus 2 squared, x plus 1. And it's asking us to sketch a graph of the function factor first if the expression is not in factored form. So, okay. So that means this is at x equal to 1. So we know we've got a 0 at 1. And its multiplicity, let's just write this out. So we can, that'll tell us if it cuts or not. So it's an odd multiplicity. This is equal to a -2, and it's an even multiplicity. So it cut, the odd cuts, the even touches. So, and that's at -2. And then this is an x equal to -1, and it's an odd, not because 1 is odd, it's because the multiplicity, the exponent is odd. And so it cuts at a -1. So this is -2, and this is -1. Okay. And the degree is the exponent of 1 plus 2 plus 1. So it's 4. So it's even. So it's either going to be both up or both down, right? It's this or it's going to be this. And the leading coefficient. Isn't it so cool that we can do all this from the symbolic function of this without even seeing the graph yet? We can visualize the graph. So our leading coefficient, because these are all +1 up here on these x's, it's going to be 1, which is greater than 0. So it's going to be both face up. So it's going to end facing up. That means it comes from up here on the -2, which it touches. So it's going to come down, it's going to touch, it's going to go up and do something, right? Because it's just touching. It's going to do something up here. I don't know how big it's going to go up or go down, but then it's going to cut through at a -1. It said it cuts. Right here it cuts. We need to know where it crosses the y-intercept. And because it's a degree of 4, if you take 4 minus 1, it's going to turn 3 times, at most 3 times. So 1, it should turn, it turns there, so it turns here, it turns up here somewhere, and then it's going to turn at the y-intercept. So the y-intercept is going to be 0 minus 1 to the 1, 0 plus 2 to the 2, and 0 plus 1 to the 1. So this is going to be a -1 times 4 times 1, which is a -4. So our y-intercept is at 0, -4. So that's going to be down here. So it's going to go down, hit the y-intercept, come up, go through 1, and end like this. Let's go check it out. easy. You can tell your parents. You should go through and tell your parents this. And then you've crushed it. So I'm going to turn off our previous graph. This is going to be number 92. And it's y equals, we have x minus 1, x, no, I bumped it, x plus 2 squared, and then x plus and it looks like what we thought. How cool is that? There they are. And there's the y-intercept. So cool. So cool. Okay, let's go back to my paper, and we have one last problem to get through, and you have learned so much in this lesson. This lesson is jam-packed. So last problem is number 102. This one is they're giving us information. We're going to put it all together. It says find an expression for a polynomial function with the given properties. So it, number one, it has to have degree 4, zeros at 2, -3, and they each have multiplicity of 1. So that means this is, and then this one is multiplicity of 1, and then a 0 at 5 is multiplicity of 2. So that's x minus 5, and that's squared. And this is 1 plus 1, and 2 makes the 4. And so it doesn't say we have anything different on our leading coefficient. So we're going to assume that this is it. X minus 2, x plus 3, x minus 5 squared. Isn't that so cool? So it tells you where the zeros are. That's your x equals. And then you're going to move them back by subtracting 2 and setting that equal to 0. And then move that back. So it's x plus 3 equal to 0. And you're going to subtract 5. So this is x minus 5 equal to 0. And I hope you learned a lot. Catch me back for lesson 3.3 here in a bit.